Welcome back to our Software Design Development Unit. In this lesson we will look at evaluation. Our learning intentions for this lesson are as follows. We'll learn the criteria that a development team will use to evaluate the success of a software solution. As always, we have some success criteria to follow. For today's lesson, they are as follows. I can describe the 5 pieces of criteria used to evaluate a software solution. I understand how to develop a software solution using the 5 pieces of criteria used to ensure its success. I can evaluate my own solution using the criteria set out. When we evaluate code, we will look at certain criteria. It is important to remember, although we will discuss the criteria and what the criteria consists of, we must understand that we should apply this criteria to our software solution. When we complete a program, we must meet the requirements specified at the start of the project. This is known as being fit for purpose. These requirements are identified during the analysis stage of the iterative development methodology or requirements review sessions during each sprint of the Agile software development methodology. How do we know a program is fit for purpose? Well, that program will be evaluated against agreed functional requirements, scope and boundaries to ensure that all the program's elements have been implemented as expected by the client. The first thing we'll look at when evaluating code is efficiency. A software solution would be considered efficient if it minimises the unnecessary use of resources such as processor, RAM, hard disk space and internet bandwidth. Creating efficient software can be a time-consuming process, and that can lead to longer development times. That becomes a trade-off between development time and efficiency. Very occasionally, a software house may find it desirable to release a fully functioning yet inefficient program. That potentially reduces the expense of development time and allows the program to start generating revenue. However, this is balanced against the risk of releasing a suboptimal solution which might not satisfy the client. When programming efficiently, we must consider the coding constructs that we use. For example, a linear search. An effective programmer would be aware of the characteristics of the iteration constructs to create an optimal solution. Would they use a fixed loop? Would it be a conditional loop? A while loop when the condition is checked at the start of the construct, or a do until where the condition would be checked at the end? All of these things would need to be considered. Here's an example of a linear search algorithm that's not optimised and is not the most efficient. We're using a fixed loop here for the entire length of the array. In this case, we're looking for the value 44, which we can find in the 5th element of our array at index position 4. However, our loop performs 5 redundant iterations after that value has been found. This makes this algorithm inefficient. Let's now look at a more optimal solution. In this case, we're using a conditional loop where we are using 2 exit conditions for the loop, one being iterating through the entire array and having the last index position in that array as an exit condition, or we have a boolean variable which is turned to true if we find our search value. Again, our search value is 44. we find that in the fifth element of our array, index position 4. In this case, found will be set to true, and that will terminate us from the loop. This means we will only do 5 iterations of this loop. A much more efficient solution. Modular programming can also help with efficiency. The use of functions and subroutines makes our code shorter. It utilises less RAM to reserve variables and data structures. Memory is reserved for procedure scope data at the start of a procedure call and then released at the end of the procedure call. This minimises the amount of time that data stays resident in memory. In this example, a program performs 2 searches by calling a search subroutine. The memory required for the search phase is reserved during search and then released when it is complete. Again, this leaves more memory available for the other processes when the search is inactive. In this example, the 2 searches are completed by following a repetitious sequence of code. The memory required for the search phases is reserved at the start of the program and is kept in reserve even when the search is not active. The memory is not actually released until the entire program has been executed. Careful use of conditional statements is also important. These evaluations make particular use of processor resources like the registers and ALU processing time. Minimising the number of evaluations frees up our registers and ALUs for other work. In this example, we're using a grading algorithm. It's not an optimal solution. The reason for this is that all 4 conditions are evaluated regardless of the mark value. We now have a more efficient solution. If the mark value is less than 50, a maximum of 3 conditions are evaluated. If, however, the mark value is greater than or equal to 70, then only 1 condition is evaluated. This can result in a 4 times reduction in ALU load against that suboptimal solution that we looked at earlier. As well as constructs, we must also think about memory and variable types. We must think carefully about the type of data that's being stored to ensure we select the best options. In our example to the left, the storage requirements for variables declared in Visual Basic Programming can be seen. As we see, for example, a real number single precision variable of 32 bits is half the storage requirements of a variable declared as double. Careful selection is important. The next area of evaluation we'll look at is usability. The user interface in a piece of software is vitally important. It must be designed with the target audience in mind. Our user interface should be customizable, appropriate, consistent. It should provide protection from error, and it should be accessible. When we look at our user interface, it should be customizable so that users can alter the way they use the software to their own preferences. It must also be appropriate to the expertise of the user expected to be using the software. If it's too busy or too complex, a standard user may find it difficult. Our user interface should be consistent so that users can find similar functions grouped together under menus and in the same place. It should provide protection from error so that critical events such as deleting data give sufficient warning to the user before they are completed. This gives the user an opportunity to opt out of that operation. User interface itself should be accessible so that its design does not impede those users with disabilities. We may have built-in functionality for people with visual or audio impairment. These are just some examples. Maintainability of our software is also important. This means it's easy to modify or adapt if necessary. That's why readability and modularity are crucial in software design. The person who wrote the code may not be the same one who maintains it, and the original programmer hasn't written it clearly. They might find it difficult to understand it later. We make it maintainable by including internal commentary, by using meaningful variable names, meaningful function and subroutine names. We make good use of white space and indentation, and also the capitalization of keywords. Modularity can make our program much easier to maintain because the separate functions can be tested and changed without causing any interference with other parts of the program. It's also easier to locate and correct errors within a modular program. Maintainability in a modular program would use subroutines and functions for common algorithms and code, which is likely to be repeated and used frequently. By doing this, we minimise the scope of variables and data structures to ensure that it's easy to track declaration and usage of these variables and data structures. We also must ensure that our program is robust. Software can be considered as being robust if it's able to cope with mistakes that users might make or unexpected conditions that might occur. These should not lead to wrong results or cause the program to hang or crash. A robust program is one which should never crash. We make our programs robust by guarding against incorrect input. We would include error checking code such as input validation. We would use built-in functions to convert data types before we process them. And we'd also design the user interface so that the user can select items from a drop-down list or a menu rather than typing in the values. Thank you for watching this series of lessons. Please subscribe if you haven't already done so.